Hello everyone. Now this time we're going to begin into cylindrical coordinates. Now I know you're tired of all these systems. You're like, I'm tired of equations of motion. I don't want to see them anymore. They're all the same equation, just with different subscripts. And I get you. However, it's best to get them all out of the way. Then you don't have to worry about them anymore. You'll just have to use them. So, cylindrical coordinates, it's very similar, at least externally, to our normal and tangential method. However, this path is typically more complex. For example, in this case, it's moving in 3 dimensions all at once. Now, in our cylindrical coordinate system, we have the r, we have the transverse, radial transverse, and our z coordinates. And we can then write them simply as we had before. However, we have to remember that the acceleration in the radial direction and acceleration in our transverse direction are not just simply, a time derivative. We have a lot more complexity here. With that complexity can come solutions, because typically you're studying a complex situation, and all of this is kind of given to you. You'll know what the radial direction is and how it changes. You'll know how the angle changes, or maybe the rate of change of the angle. And so these aren't too bad. You just need to write them down and know where to find them so you can look at them, reference them whenever you get to a problem that needs them. Now, if the particle is constrained to move only in the r transverse plane, so that's the z coordinate is constant, then it's more or less just polar coordinates now. And we only have 2 equations. Our z direction, some of the forces in that direction are equal to 0 because there is no acceleration in that direction. Now, one thing we have to remember is that with the nt coordinate system, even though these look kind of similar because it's a nice curvy path, this is a fixed coordinate system. We have an origin, and that origin does not move. It stays in the same spot. Now, I freaked you out here. I know I did, because I suddenly started talking about tangential and normal forces. Tangential and normal forces. And that freaks you out because you're like, wait a second, this isn't the nt coordinate system. And you are correct, okay? You are correct. However, what happens a lot of times is we will have a force that is going to be accelerating it that will be tangent to the path, okay? That will be tangent to our path, which is fine. And we'll have a normal force in exerted by the path on the particle. So where this becomes really kind of hairy is I don't know what this direction is necessarily, and that direction kind of frightens me. And this one also. None of these are along our radial or transverse directions. And so it would be very, very helpful to know, well, what is this angle between my tangent at that current moment in time and my radial direction? What is that angle? We call this angle psi. Now this has a nice little equation right here. And I'm not going to even try to go through this right now. You know what? No, I'm not gonna back down. I'm not gonna back down from this. I'll go ahead and try to explain it for you. Though it's not always the easiest to see. So we see that we're getting this from a tangent function, which is always opposite over adjacent. Opposite over adjacent. So opposite in this case is right here. Let me make sure I get this one right. Is right here. Is a failure. Okay, now, in all honesty, it would probably make a lot of sense for us to teach you how to calculate this angle psi, right? Just to expect that it would work. Now, there's a nice simple equation. It's right here. However, let's look at where that actually came from. Now, remember, we're calculating psi using our tangent function. It's always opposite over adjacent. So let's zoom in right here and figure out what that means. Now we have, more or less at this point, I'm going to try to zoom in a little bit right here. Okay, got that. Our tangent line, we have our perpendicular line right here. Okay, that's right angle. And then we have this point. Now this is the radial direction at one point in time. This is the radial direction at the second point in time. And now let's get rid of this. So this side right here is r d theta. For a very, very infinitely small moment, we can say that this is equivalent to the path length, even though it's going to be a curved line. We're saying it's perpendicular, or just this perfectly straight line, because it's infinitely small. And then this length right here is going to be our change in our radial position. Our change in our radial position. dr, which once again will be exact as long as it's sufficiently small. So if this right here is psi, then that angle right there must also be psi, opposite interior angles. And so therefore we have opposite over adjacent tan of theta. And we can rewrite that if we want to, like so. So if psi is positive, it's measured counterclockwise from the radial line to the tangent. If it's negative, it's the opposite. Okay, big thing to remember here, tan of psi, radius over the change in the radial position with theta. Oh, so that'll be enough for this time. Next time, we're going to jump straight into an example. So thanks for listening. I'll see you all later. Bye-bye.